Hello and welcome to our next episode of Chaos and Caffeine. In this episode, we're going to cover some information on standards, what they are, what they aren't, but we're going to focus on electric motor repair standards, what's coming, what is in process, and some future ideas that are being discussed actively within the standards community. A lot of this is being driven because while there honestly hasn't been too much change in what's going on, there are new ways of looking at that data, the data we've had. So, and of course, with new materials, what those results look like. So we are going to start, of course, by testing another K-Cup style coffee. And this is a breakfast blend, so I'm assuming it's a relatively, I don't know, I think it's more of a medium blend. I don't have the box this time. It's an Entenmanns coffee. And so basically it's being made for a restaurant. So it's being made by somebody else, I'm sure. They don't make their own, as far as I know. But in any case, let's go ahead and give it a shot. This, of course, is available in most supermarkets and so on. So let's try it. Yeah, definitely kind of a lightish coffee. Yeah, nothing super, but it's okay. It's going to be a normal caffeinated coffee, of course, which means I'm going to have to reach down and grab something else at some point. I still give it a thumbs up. I can, if I were to be in a hotel or a restaurant and they served me this, I'd probably be fine with it. I think next week I'll try the Kona blend that's used at one of my favorite lunch restaurants, but neither here nor there. So, good stuff. So that's what I'll be sipping on today with a backup of Valhalla coffee from Death Wish. So, let's get into standards. We're going to focus primarily on IEEE standards, and in particular, we're going to cover the standards that are associated with basically testing and how we interpret stuff for when we are testing, insulation testing, and so on and so on and so on. So I'm going to start with one. This is, you'll notice that it says P62.2 Draft 7. So this is not out yet. As a matter of fact, it is now out for vote, and I believe we finished all of the comments. I believe this one is a clean draft. It's in Word, but this one is the Guide for Diagnostic Field Testing of Electric Power Apparatus, basically electric motors and generators. We'll get to the scope here real quick, and I'll cover what it is, and then we'll go through a few things. Now, one of the points with 62.2 is it provides a little bit more, there I am, a little bit more detail on how to interpret things. So we'll cover that in a minute, but just to give you an idea, some safety-related stuff. And they're not going to go too far into safety. Things about personnel and equipment. The guide to maintenance inspections. Now, this and IEEE 1415 are going to be very close. So when I'm working on 1415, we'll cover that next. I'm the chair of 1415. We're going to be looking at all of this, and because part of 1415 is developing a condition-based maintenance program or predictive program or periodic testing, basically. This does something very similar. It is more open to, so let's go through and we'll say general related documents, inspection and test techniques for the stator winding core, and then rotors inspection techniques for the AC machine assembly, and you'll see then it goes into DC. So that means both motors and generators, AC and DC. So the idea here is this is supposed to be kind of an encompassing testing method. So let's get into the scope. This guide describes offline inspections and diagnostic tests which are performed in the field on rotating electrical equipment with voltage ratings of 3,000 volts and higher. So you notice it's not random wound machines anymore. Matter of fact, a majority of standards that are coming out are focusing more and more on form wound. And this caused a little bit of confusion in a discussion I had recently with 522. There is, well, we'll cover that in a few minutes, but there is some stuff with 522. I had mistakenly thought one way, and you know, that happens. These evaluations procedures, which are common use on large rotating machines, have been found prudent in assuring high equipment reliability at low overall maintenance cost. So again, this and 1415 are going to be relatively close, except 1415 goes the next step into root cause analysis. So let's take a look at an example. Scroll down till we find something. You know, so there's a lot of whatever, and here's diagnostic charts. Provide the user with a means of identifying applicable testing procedures. So if I'm looking at synchronous motor induction, so A, B, C, and D, you'll notice it takes me to different sections. So visual inspections, wedge tightness, da-da-da-da, all this stuff here. That one's going to be interesting because I've got a question on that that I have to answer. And we'll go ahead and we'll answer it on here. Here's one for diagnostic tests. You notice these are pretty standard. One of the things that we did do, I came in a little late on this, so we did discuss including electrical and current signature analysis in the working group, but it was a little late. It was already getting ready to go up for vote. We could not delay it any longer. The next time it comes around, which will be within 5 years, we're going to have more backup data through CGRAY and some other stuff we're working on, and 1415 to then include the ESA stuff and current signature for AC and DC machines in 62.2. You'll notice that there are some things that you would expect to see, like for instance, they do have bearing insulation tests, they have eddy current, ultrasound, but you'll notice there's no mention of things like vibration analysis, which should technically be in here. Will be in 1415, which is a completely different document. This is primarily electrical tests. So personnel qualifications, hazards, et cetera, very vague, by the way. You're going to find that there's not a lot of conclusions in here. There's some guidance, but that's going to be about it. So we have to go down to section 7, because that was all the stuff. So stator winding, visual inspection. Let's take a look at this slot portion. So bar slot vibration, look for dust or grease, bar slot discharge. If bars are free to vibrate in the slots, severe degradation of the ground wall insulation, and it'll of course reference you to the appropriate standards, such in this case, partial discharge, which the ozone attacks the material, which everybody says there's powder there. It's not powder, it's bleached insulation. A lot of pits that make it look whitish. Bar vibration, sparking, wedge and filler vibration and movement, basically looking at loose wedges, etc. Now, this is an area where electrical signature analysis and current signature analysis really have some strengths for coil movement as well as magnetic wedges in particular. So, here's some suggestions that are built in. This is the version that's out for vote, so, or has been voted on. No, out for vote. Here's checklist for what to look for. So a lot of visual inspection stuff, you'll notice that in a lot of IEEE standards. We rely on visual inspections more so than the electrical tests. Now that's important to understand because, and we're going to get rid of this now and move on to the next one, but that's important to understand that, the visual inspections carry more weight than your standard electrical inspection. So if I have a surge test performed, but I see a damaged insulation system, which carries weight? Well, I've had people argue with me that to move forward because, it passed the surge test. Well, I'm sorry. When it goes into operation, it's going to fail rapidly because visually it's failed. Dry and brittle and all these other conditions are very, very important to notice. So for 1415, I'm going to show you the old version. The reason I'm showing you that, here's the par here for the new one. I think I talked about this in a previous standards discussion on chaos and caffeine. But I basically, if I had taken this over because it was dragged along by the previous chair, if I had allowed it to continue to be dragged on, I would have had a year to fix this, and it requires basically a major rewrite. It's supposed to have troubleshooting charts and so on in here, and unfortunately it spends more time on the testing methods because everybody got their stuff in here, and the entire failure tree is a page. I'm sorry, but we need far more than that to understand, especially root cause analysis. It also doesn't have a true root cause analysis methodology in here. What it basically has is a checklist of what tests to perform, but not how to utilize those tests in order to come to a conclusion. It does have vibration spectra and a bunch of other stuff. It's missing some new technologies and new methodologies, which are finally out, by the way. So let's continue. So 1415, of which at the time I was, did they list me right? I was the secretary at the end. We didn't have anything there, so there I am there. Those are the people that voted on it. We got it through. It covers all kinds of stuff in here, including, basically the original scope was for form wound machines, and it stays as such for induction motors. And then it says form wound squirrel cage. Now, I've changed it a bit so that it is induction machine. Provides means that the guide addresses the following machine systems: stator, rotor, vibration, bearings and shaft, structure and frame, ventilation, and accessories. We did not. I'm sorry. I changed it to cover also wind turbine generators, induction generators. There's some verbiage in there that was supposed to be corrected, so that should leave out the squirrel cage requirement. So we will have doubly fed induction generators and squirrel cage wind generators included in this. So as we go through, references to other standards, we're not necessarily, and some of those standards, really, we selected them. Like I think there was, how to do different types of measurements, like 118 with drawn and stuff like that. So we have new standards that cover some of that, and a bunch of other stuff. So the maintenance inspections, that was where we got into the descriptions. And one of the things I had a problem with was it got broken down into individual components of a test. So AC high potential, which is, that one would be separate. Potentially destructive. Potentially destructive means if it's not performed right, the amount of electrical pressure applied could damage the machine. So let's get out of this one, and we're going to get into a few others first. Here, let's see. Yeah, so let's go ahead and we're going to cover Some of the ones that I think you'll find particularly interesting, 97. So this one, 97, this is a new one. So it says draft trial use guide for advanced diagnostic techniques for insulation testing of AC machines using direct current. Okay, so what does that mean? Well, this is the standard where we finally include insulation resistance profile. Let's get down here. And we also include some other stuff like how to perform your DC ramp test, and also your polarization depolarization test, which, to be perfectly honest, prior to this I hadn't heard of. It's something done at Hydro-Quebec and some other places. It was introduced, I remember when it was introduced, like in the early 2000s. It was discussed in the group and to include in the 2013 version of IEEE Standard 43, which we'll cover next. And then here we go, insulation resistance profile. This is basically the insulation curve. I don't know how this turned out in this edition yet. I haven't had a chance to look at it. Our next meeting's coming up. Here we go. So a lot of these that's polarization and depolarization. So that is basically a lot of examples. And yeah, notice color. Yay, no black and white. So all the different things and what they mean. So this is further testing related to that. And then we're going to get down to so PDC polarization index. So the effects on PI, that's PDC curve still. Sorry, my bad. Here we go. Insulation, aging, etc., lack of curing, insulation resistance profile. It's a graphical representation of various insulation resistance versus time in which the shape is used to analyze as the analysis tool. Why is this important? Well, because as we'll discuss with 43, insulation resistance testing by itself is not meant to condemn or pass a motor. I've seen some bad information showing up on places like LinkedIn where people are going on to ChatGPT or equivalent and capturing wrong information and presenting it, trying to show themselves as experts. Very, very, very sad. But here's the test. So insulation resistance profile, the overview. They're very similar to the PDC, one that I just breezed through and we didn't talk about, but that's supposed to be charging and discharging and how the curves look and how long it takes to discharge. It gives you different indicators. However, most people have access to this type of test, whether it's through, say, a PDMA or I use an amp probe, high voltage tester, that kind of thing in order to get the curve. So we came up with, at least 10 minutes. It can go longer. So there is a calculation for how long to go. It's basically till the curve flattens out. You want to do that because discharges occurring in different spots indicate different things. Some of the stuff that you have to worry about, the usual stuff. We've done something special with a lot of these standards now, and that is we spend more time describing things instead of saying, this is this. We say, here's why we do this, here's what's going on with the system, and we're doing that because of the transition as we're watching all of the folks that know this stuff leaving the industry through retirement or passing away. In this particular industry, mostly people who leave, like the standards group and stuff, it's because they can no longer physically participate or they're gone. A lot of, as a matter of fact, all my mentors from the early days, or some of them, a lot of them are still alive within, say, the PES materials group. they they're still there, and they've retired like a decade or more ago. So we've got a lot of old gray-haired folks, and I think I finally qualified for that. Although I'm still one of the younger folks in the group, which is really disturbing. In any case, healthy insulation exhibits insulation resistance profiles that are smooth and continuous like this. So this is an example. As we continue on, okay, there's parts supposed to go in there. We start looking at different types of things. So form wound type of machine, this is contamination or moisture ingression. And then contamination, this would be, I think this looks like a PDMA output. Yeah, and there's the machine. I think this one is from, I know these are from mine. This is from a rotor on a synchronous machine. I've done presentations on that. And then severe contamination, I think this is also one of mine cases. Here's another one, thermal aging, where it's smooth and then it starts discharging, go up. And you notice the insulation resistance is actually relatively high. And that's the whole point, is this test allows us to take a look at those conditions. Here's an uncured, cured versus uncured. So here's an example. This was a larger one. This is a smaller hydro generator, in which you can see one curve is quite low. That is the insulation where we actually put this is mine as well. We had put a special type of liquid insulation in there that's a penetrant. It's supposed to fill in all cracks and stuff like that on an aging insulation system. I did it on one phase in order to generate this back in 2010. And then this is what it looked like after it dried. So yeah, so different situations. Basically, a lot of case studies as to what's going on. So that is a big one. That one is coming out soon. Should be. Yeah, I think we've got lots and lots and lots of lots and lots of reading material to go with this. I think Dave McKinnon and I did quite a bit. Let's see. Oh, okay. Here we go. Yeah, IRP section. It's almost all Nancy Frost, Dave McKinnon, and I doing a lot of work on this stuff. So a couple of them are from presentations I've done in the past in order to continue on and develop, because you need references. You need not just random magazine articles. And, I can't go in and say, oh, yeah, I got this off of Reliable magazine, or I got this off of, Plant Services or whatever. We have to go through peer-reviewed, so a NETA article, IEEE, something where somebody else has taken a look at it. So let's move on from here. That's one of the big new ones. There's a lot going on in form coils, and this is something that is a bit of a concern, is very little going on with random wound machines. Another one here, 56, is IEEE Guide for Installation Maintenance of Electric Machines. We had a slightly different title before. This is the new one. This one here is undergoing revision right now. Anything that's 5 years starts into revision. Yeah, there I am again. Yeah, I notice I'm in an awful lot of these. Lots of references. This one goes into things like how to inspect, how to look at visual inspections of basically all the components in the machine, like what the insulation system should look like, and then some testing. So this is, and here's the LCID here. Stator core interlaminar insulation test procedure. That would be your core loss test. However, that's being superseded by a standard specifically meant for core loss testing. And we're going to cover that in a minute, but let's take a look here. Visual inspections, basically how to look at an armature winding, how to look at, here we go, partial discharge, rotational forces, basically a description of what you're going to see. Now you notice that it's only like 1 or 2 sentences. What's going to end up happening as we finish this one, that's going to build out into much more information. As I said before, we have determined that we have to be more descriptive and spend more time on what you're looking at, pictures, guides, other things, as we're transitioning and the history is going away a little bit. Let's see what this one here is. Dissection techniques. Oh, for 1415. Yeah, so the new 1415. One of the things that we're working on right now. We just had our meeting the other day. I missed that one. I'm going to be in the next one. I can't miss these because it is so important. This is the one where we're discussing and coming to agreement on dissection of form coils, primarily. I believe we have snuck a few extras in there. It's a Nancy Frost one, of course. And it's going to go into all kinds of cool stuff. Let's see. Root cause analysis. Okay, so basically the steps for doing it. Layer by layer peeling. Thermoplastic, different types of insulation systems, random wound windings, and small form wound coils. These are going to be annexes, meaning they're not part of the main body, but this gives us the ability to come down here and take a look at, how to dissect small motors. Okay, and this is something that has been badly needed. So how do we do that? And that I found important for a couple of reasons. Labeling bearings and coils, where is it? There should have been one in here, unless we have to include it still. Okay. Yeah, because there's one I wanted to make sure of. Root cause analysis. Oh, okay, it's just the references. I want to make sure of because, here we go, examples, of course. We're looking for, we're picking up more images, and so on and so on. This way, if I'm in the shop, in a repair shop, or I'm a consultant and I want to do my sectioning, I can do that because pretty much the OEMs, and I had this pushback recently in a project I'm working on quality of manufacture, and the quality wasn't the greatest from this one manufacturer, and they came back and said, oh, well, they're not qualified or they're not allowed to do coil dissection because we're the OEM and only the OEM is allowed. That's why this exists. The challenge I run into is, I work with a lot of OEMs, but I will say often if you question their quality, they become bullies. There's a reason for that, of course, but in reality, this is part of the reason why we set up standards. So if I'm going in and I'm defending a client, and I'm saying, hey, this failed because of this, and I just did another one where we went to a repair shop, we said, okay, this failed at this point because the coil wasn't brazed properly at this point here. Here's how we determined it. Well, then I'll have a guide to reference back to, in addition to the RCFA stuff. So that is going to be tied to that. I mentioned stator cores, so this is the other one. So this is, of course, with it saying 1 MVA, that is a much larger core size. So that is your bigger machines. And of course, it's going to go through all kinds of stuff. Okay, I still have to be added. All the standards, how to evaluate core losses, etc., etc. So some references over to IEEE. Very large. Basically, it's meant for generators. So we don't have a lot of representation for smaller machines. What we'll do usually is reference it back to IEEE 1068 or ANSI ISA AR100. Okay, so this is the one draft recommendation practice for AC electric machinery with basically high pot testing. This is where you apply high DC current to the stator and you measure leakage across to the frame. This is scoped for high direct voltage on motors 2300 volts or higher. So you notice it's not low voltage testing. Why is this important? Well, we're going to try to include some stuff in 1415, even though it's also meant for form coils, because there's no standard for this stuff for low voltage random wound machines. In IEEE, there's NEMA, but that's about it. So let's get into 43. Okay, so it was called a recommended practice. Now it's a standard, meaning it's now bigger, badder, bolder, and it says you shall instead of you should, that kind of thing. So when I come in here and I'm taking a look, you'll notice when we get there, there I am again. Just to say, I speak from authority on this stuff. Okay, so we're working on it again. As you can see, the reason why all this stuff is I pulled it right off of the site. So this is the latest and greatest draft. We're spending some time on this. It gets really wonky when we get into PI, and instead I reference you over to 97. So what are the components, what, et cetera, et cetera. So good, solid description of what's going on. And then here's the big part. So effects of different conditions. There's also another one. So what happened some time ago in this is they said, oh, you can't do rotors. Well, Army Corps of Engineer came back and said, we do rotors. So therefore, we want to have it in the standard. And so now it's getting added, hopefully, to the standard. Okay, winding connections. So here we go. Recommended when feasible that each phase be isolated and tested separately. Separate testing allows comparisons to be made. That would mean that in a AC motor you would break the Y connection. You're not going to find that in most small machines. So this is meant for larger machines again. Again, most of the people sitting on these committees are oh, did I miss it? I did. Impact of temperature. Yeah, here we go. That's what I was looking for. Surface condition. Okay, so contamination, oil, carbon dust, etc. Effect of moisture, effects of temperature. Now, I don't believe we included in this and how to correct for temperature. So you notice this here. There's different types of changes based upon the type of material being used. Tends to happen, you tend to have to correct at 40 degrees centigrade and higher. So if you are testing a cold winding, that's better because then it's an easy, the doubling for every 10 degrees centigrade or halving type calculation. So calculations are all here. We do get again into more descriptive stuff. This is how to measure it. and how to interpret it. Okay, so one of the big things, insulation test data is useful in evaluating the presence of some insulation materials such as contamination, absorption, or severe cracking. However, limitations are as follows. Insulation resistance of a winding is not directly related to its dielectric strength unless the defect is concentrated. It's impossible to specify the value of insulation resistance at which the insulation system of a winding will fail. So that is my pushback when I keep seeing these people saying, oh, well, at 100 megohms, that's when we replace the stator. Why? What I would say, okay, you've hit that point, and by the way, for a low or high voltage motor at 100 megohms, you can go ahead and perform the other tests to see if this is an actual condition. Why not perform an insulation resistance profile to see what's going on with the machine? But no, people are going to condemn perfectly good machines for this, right? Windings have extremely large end arm surface areas. Large or slow speed machines, wound rotor field windings, or machines with commutators may have insulation resistance values that are less than the recommended value. In these cases, historical trending is invaluable in evaluating the system. A single insulation resistance measurement at one particular voltage does not indicate whether foreign matter is concentrated or distributed throughout the winding. Direct voltage measurements such as IR and PI tests may not detect internal insulation voids caused by improper impregnation, thermal deterioration, or thermal cycling. So basically, the one thing that this one person posted on LinkedIn, this is saying everything he said is completely false. I didn't put this in there. I vote on it, and I'm part of the discussion, but this section was somebody else. When insulation resistance tests are conducted while a machine is at standstill, these tests will not detect problems due to rotation, such as loose coil. Basically, it's saying you can't tell winding issues or other conditions with insulation resistance. Why is this section here? Why is 11.3 here? Because of all the BS that's spread by people that don't know anything about electric machines, that pretend they know things about electric machines. Okay? Here are a couple of suitability for continued testing. When the insulation resistance history is not available, recommended values of PI or IR may be used to estimate the suitability of the winding for application of an over-voltage test for operation. Okay? If the IR or PI is low because of dirt or excessive moisture, it may be improved to an acceptable value by cleaning and drying. Okay? When drying insulation, the PI can be used to indicate when the drying process can be terminated. If the IR is low due to severe insulation deterioration or damage, operation and overvoltage testing of the machine are not recommended. So if I have a low insulation resistance, I just don't perform the high voltage test. And in all of your automatic tests, that's what happens. It comes up, it goes click, turns off. Okay, mind you, I do force them sometimes just for fun to see the little lights. Insulation resistance. Okay, here we are. This is the big question, right? For windings made before 1970, and all field windings, and others not described below, 1 kilovolt plus 1 megohm per kilovolt plus 1 megohm. So 1 megohm plus 1 megohm per kilovolt. So 480 volt motor would be 1.5. Now, here's what's really important about this. Temperature corrected to 40 degrees centigrade. That's the other thing I keep seeing out there. If you're going to start talking about testing, learn what you're talking about before you start misinforming people on the internet. That's what's dangerous about the internet. Okay? I like to go back and say, here's the results. This is why. And if I strongly believe in something, I go in and I work on a consensus standard with people that are also in the know. So we come out with something, we have a consensus agreement, not rule of thumb because some guy heard this somewhere on a train with a bunch of people that were mechanical engineers that are talking about insulation testing of electric motors, or, my favorite is the expert florist or nail thing. All the weirdness that's going on the internet now, all these experts in this stuff. This is only part of all the standards I'm involved in and all the other stuff I'm involved in with electrical systems, let alone electric machines. So, the minimum insulation resistance for overvoltage testing or operation of AC and DC machine motor windings and rotors shall be determined from table 4. So, for overvoltage testing, okay, the actual winding insulation resistance used for comparison, and the insulation resistance of one phase with the other two phases could be lower than 3 times that of the entire winding due to phase-to-phase contributions of the total current. So you can't test one phase at a time and then add them together. Okay? So this is meant to determine if you're going to go on to higher voltage tests. I will say things like in the military, in the Navy, we had a 1 megohm limit. Coast Guard, 1 megohm limit. Okay, here's the PI thing, all the stuff going on with that. The blue means that, oh yeah, we had comments, more comments. This is the rotor windings. It says field windings. But that's about it. So those are some of the things to be concerned about, and that's it for that. Let's just cover a few more quick things here. IEEE 1434 is the guide for measurement of partial discharges in AC machines, and that one is relatively new, 2014. We're just redoing it. I think we just put it out for vote. It offers no pass-fail criteria. 1799, recommended practice for quality control testing of a partial discharge or of external discharges on stator coils and windings. 1799 is the first one to provide clear procedures and acceptance criteria for visible corona discharges on stator end windings. So basically, I'll refer to that to a few things. So now, IEC standards, which I didn't cover, there's 60034-27-1, which is offline partial discharge measurements on winding insulation or how to perform offline PD testing. And it does include some guidance, but no acceptance limits. 60034-27.2, online PD measurements, again, the same thing. It gives guidance but no conclusions. And then IEEE 2465, which I didn't cover on here as well. Trial use recommended practice for pulse type PD measurements on stator coils and bars. That's designed to evaluate partial discharge on VFD rated motors. Then, for motor current signature analysis, there is ISO 20958, which is 2013. I haven't heard anything about work on it. I was originally involved in it. That got scrapped, and then other people hijacked it. But that's neither here nor there. Basically, 2008 happened, and all the work we did was thrown out, and other people got involved. We talked about it separately. 1415, we talked about. There's some other ones. Surge testing. IEC 60034-15. Impulse voltage withstand level of form wound stator coils. Much like 522 and IEEE. IEEE 522 Guide for Testing Turn Insulation, it has, it covers, let's see if I can go find it here. I have my whole standards library. Oh, 2023 version, I do have it. So let's go take a look. There's some important stuff here. 43 we covered, 286 power factor tip up, and there's also some other related stuff. So here's 522. We'll cover that in a second. Ongoing, I was going to cover that next. So let's cover this real quick. Here it is, section 7. This is the one that caused me some confusion as well. And let's go ahead and get this a little bit bigger here. Okay, so the applied voltage for maintenance tests made in the field may be approximately 75% of V test is defined in clause 6. So let's come back here, and this is where they get into it. 3.5 per unit, so that's 3.5 times the voltage rating of the motor. So a 2.3 or 2300 volt would be tested at 6600 volts, 4 kV at 11.4, etc. Calculation for that, 2 per unit surge test. This one here is a lower application, but so this would be machines that are not going to watch closing and stuff like this. This would be for, so the idea behind the surge test is the withstand should, circuit bounce and other things that could cause breakdown of insulation. This would be for soft starts, and then how to reduce that. If it's a machine in the field, you do 75% of whatever that value is. We used to use twice the voltage plus 1,000. I have not seen that in a little while here. It's often used still as a rule of thumb. So now we've covered that. Oh, here's the other standards. Okay, this is the surge test one for surge PD, and this one here is mechanical vibration. So this is an IEC 60034-14. This is your machinery standards. Which one's this? This one here is how to perform root cause analysis. Why did I bring that up? This one here is online detection diagnostics of potential failures in active parts of and of bearing currents. So this one here is a standard on the detection of different types of things. So when I'm working with the Empower MCSA device, I'm referencing over to this standard. So this one was 2009. 1068, here we go. So this is a standard for the repair and rewinding of AC motors, and it does include sections related to surge testing of insulation systems. I wasn't on this version, and that was a problem. I was kind of kept off of it. And it allows now for a 20% increase in core loss per repair, which I find interesting, seeing as I keep being told that I'm wrong, that there is no increase in core losses through the repair process in public, but the same organization that's been making that statement is the same organization that insisted that 20% be included in here. Go figure. Bearings and fits. Field repairs, so we want to go to electrical evaluation. So this is all the inspections, insulation resistance, DC voltages for different things. Dielectric absorption, full stator. Where's the surge test? Here it is. Sets are recommended to detect. Here we go. So 460 volt would be 560, 640, or 790, 2300, 2.8, 3.2, or 4. These are much lower than twice the voltage plus 1000, of course. So it would be similar to twice the voltage plus 1000 and 75%. Okay, so wanted to get that aside. AR100 is here. This is something that we as an IEEE member have available. Includes all of the different repair practices and testing. So installation resistant, PI, form 1, Oh, pardon me. So, anyways, all the tests. The dummy rotor test. I remember that one. Sometimes had to use a little Coke can. A lot of stuff in here that's very useful. The rewind process. If you don't have a rewind spec, highly recommend it. And then last but not least, I did cover 522, so we can close out of that. I think that ends all of that stuff. There we go. So now, real quick, for the final bit, let's do a quick discussion on what's happening. You notice that there is nothing in there about IoT devices, continuous monitoring, or anything else. Reason why? There are no standards for it. So everything that's being applied right now is being applied without standards, meaning that, you get what you pay for, or beware, that kind of thing. So for wireless vibration, of course, you've got single axis and tri-axis stuff. Everybody's pushing tri-axis wireless systems. There's best practices for where you place the stuff, and you learn that from whatever vibration training you receive. Now there may be some ASME or similar mechanical standards, but there is the IEC standard on vibration that I mentioned, but basically nothing on continuous monitoring. So that's changing. We are working on those right now, looking at the list. And a lot of this, and especially AI predictive maintenance. Matter of fact, I'm taking some courses right now on the AI end from IEEE. There are AI standards. Matter of fact, there's governance standards for AI, which I find interesting that, of course, the government is saying there are no standards because the standards were consensus standards and would actually not be particularly helpful to some of the organizations pushing them. We have been harmonizing between IEEE and IEC standards to make sure that they're similar across the board. Primary difference is like an IEEE standard requires consensus makeup of different folks and everything else versus the IEC standards, which allow for OEM dominance. Now, one last thing, there have only been 2 of the vibrations magazines this year, I have a full-page advertisement in this one. I also have the main article. That is a recent article. It's one of a kind, so if you do get this, it is, cover came off. It is this one here, Electrical and Current Signature Analysis of Electric Motors and Driven Equipment. And it's similar to the IEEE stuff that I wrote, and it goes through how you're able to raid across everything. And I have several case studies in there, actually a lot of case studies in there. And we get into the relative harm index and how that is used to evaluate the destruction of components, such as the bearing. So here's an example here. I don't show the RHR. I don't believe I have the RHI chart in this. I do not. I just have examples. So I actually wrote this over a year ago before we included the RHI, I believe. Missing wedges, etc., etc. And for those who like math, lots of math. So with that, we had a lot of fun today. I've kept it at just barely under an hour. If you're watching this on YouTube, like and subscribe. I keep forgetting to mention that, of course. Hopefully this was helpful. If you have questions, please reach out or put a comment down below, and I will respond related to the standards questions that you have related to electric machines for this episode. We'll get into some of the other stuff later on. If you have any questions related to specific testing methods, and what they mean, please also feel free to ask those questions in the comments, and we will respond. That also includes if those comments are on LinkedIn, of course, so YouTube or LinkedIn. With that, have a great day. We'll see you next week. We'll have some fun next week. I don't know what we're doing yet, but it'll be interesting. Thank you very much.